on for today?
Oh, no.
It's a write out, like.
It is a write-out. Thank you for asking.
Sure.
You don't like being sent over 10 times?
Oh, the chair, yes. Oh, yeah. I got it.
All right, so today we'll finish up these slides, then we'll be finished with this unit. And, after lecture, directly after lecture, I'd like to take everyone's picture. I mentioned I'm gonna do that today. Well, then we'll take a break. And after break, we'll come back for the quiz. And I did put you in groups, and Group A will go first, Group B to follow. And then after the quiz, there would be time to do a lab. Okay, so that's the plan for today. Thyroid, okay, what's thyroid? Got two glands in one. If you look at it from the front, this gland is just inferior to thyroid cartilage. Thyroid gland, just inferior to the thyroid cartilage. In the anterior neck region. Now, so let me point to it. Thyroid means shield shape. So the thyroid cartilage is right here. Right here, it's a voice box. When you take your carotid pulse in your neck, that's the artery right there. In men, that's the Adam's apple. So this gland is just inferior to it. So the name of the gland is named after the shield-shaped cartilage that it's just below. So that's where it is. It's in the neck, basically. If you look at the front, we can see the thyroid gland. And if you look on the back, we can see the thyroid gland here. But there's these four little nodules, and that's the parathyroid glands. Four parathyroid glands. Basically, they're located posteriorly. In terms of the histology, which we covered, I went over the slide, and well, this slide is from the internet, but I put the X in the area where the glandular tissue has the follicle structure. So what would that be, thyroid or parathyroid? Thyroid. The densely packed purple cells are the chief cells of the parathyroid gland. Okay. If you take a closer up look at the follicle structure, they look like little steaks, because in this slide, the colloid stains like a flesh color. But it's surrounded by individual follicle cells. And outside the follicle structure are the parafollicular cells. Okay, so you have parafollicular cells, not to be confused with the parathyroid gland. Okay. So if we start to talk about their secretions, the colloid is actually inactive thyroglobulin. I did mention that when I covered the histology. And it's secreted by follicle cells. So it's kind of like they take the inactive hormone and they keep it in the middle. They have to extract iodide from the blood to make an active form of the thyroid hormone, which I'll go over. So I want to start to talk about the secretions. At the top it says that thyroid hormone, it's actually, I've been saying thyroid hormone. It's actually T3, T4. TH, thyroid hormone, is T3, T4. The T3, triiodothyronine, that's the full name for T3. Triiodothyronine. T4 is thyroxine. These are the full and proper names of the thyroid hormone. As we'll soon see, the active form of the molecule, the active form of thyroid hormone, you knock off one iodide molecule, T4 becomes T3. T3 is the active form. Thyroxine more or less inactive. The other hormone that's secreted from the parafollicular cells is calcitonin. So these are the hormones secreted from thyroid. That's what we got going here. So on this slide, I talk about calcitonin, the mechanism of its action. You should commit to memory that it lowers blood calcium. But this slide details how calcitonin, when secreted, can do it. You would secrete the hormone if calcium levels got elevated, okay? And then you want to lower blood calcium. So this is how. So we'll call this the mechanism of calcitonin's action. How does it lower blood calcium? Number one, you inhibit osteoclasts. Those cells, the multinucleated, they have that ruffled border where they secrete lytic enzymes, and that'll dissolve bone. Basically, you're liberating the calcium from the inorganic matrix of bone, which makes bones rigid. That would increase blood calcium. So if you inhibit those cells that break down bone, by default, you're increasing osteoblast activity. When activity goes down, so the other cell activity is higher by default. So I'm writing increased activity of osteoblasts, and what you want to remember is those cells build bone. So that's why I have that second point there. I think it's the second point. Yeah, it promotes calcium uptake into the bone because these cells are be working more. So you're going to increase calcium deposition into the bone, therefore lowering blood calcium. That's what I'm writing. Increase calcium deposition in bone. Make your bone stronger. The other thing you could do to lower blood calcium is just excrete it more at the kidney. Increase calcium excretion at kidney. So the kidney, I haven't talked about that yet. It's easy to understand. It's a filter organ. It filters the blood that it receives. Oh, sorry. It filters the blood that it receives from the renal artery. Renal artery, blood coming in. Most things are reabsorbed. You filter it and reabsorb it. You keep it in the bloodstream. So all the venous blood is all the things that are reabsorbed. And you basically saved it from losing it to the urine, things you want, like sodium, water, glucose, vitamins, other things that the body needs. Waste products and other things, you can excrete in urine. So if you want to lower blood calcium, at the kidney, this hormone will facilitate its excretion. You won't reabsorb it. Okay? So all those are ways that this hormone can lower the blood calcium. So you need another hormone to oppose that. You need a hormone that can raise calcium levels. Calcium is needed for muscle function. So this describes the mechanism of the parathyroid hormone, which raises calcium levels. This hormone raises blood calcium. Now, if you study the figure, the calcium are the little red balls that are circulating, and then the bluish colored triangles are parathyroid hormone. So when those levels of calcium get low on the right side, you secrete parathyroid hormone into the blood, and it will target bone, kidney, and gut. Now for the bone, it'll increase the activity of osteoclasts, your bone resorbers. So I'm writing increase osteoclast activity. You're going to increase bone resorption. It's a fancy way of saying break bone down and look at the calcium into the blood. Okay, so that's why they show the red balls, the calcium entering the bloodstream on this side. For the kidney, increases reabsorption, lose less to the urine. Increase calcium reabsorption at kidney. You're losing less to the urine. We say reabsorption, you absorb again. You absorb the first time when you eat it in the gut. Kidney filters it out and you reabsorb it. Okay? Third one, through vitamin D, so not directly, but PTH active through vitamin D, you increase calcium absorption from the gut or intestines. Again, this is through through vitamin D. Sometimes books will say calcitriol, another name for vitamin D. All right, kind of like grease your brain for a test coming up. For example, if you can remember parathyroid hormone, can you tell me, does it raise or lower calcium? It raises it. Remember that fact. Take a minute. We're not doing half sheets today, but look at this. Commit yourself to an answer and write it in your notes. I'll give you a minute. You know, of A, B, and C, only one makes sense to me. What do you guys think? A is correct. Why is B not good? Well, it doesn't make sense. That word doesn't make sense to me. You're increasing that activity. This would lower blood calcium. This doesn't do that. The other one does. So answer this question. And it's once again, of A, B, and C, only one of those makes sense. Calcitonin, does it raise or lower? It lowers blood calcium. Only this one makes sense. Inhibit the decrease osteoclast activity to inhibit that cell. So the osteoblasts work more. Get bone deposition of the calcium into the bone. That choice makes sense. That would increase calcium levels. You don't want to increase calcium levels. That's why only B is correct. So let's remember that thyroid hormone can also boost your metabolism. So I did mention T3, T4. I did mention T4 is more or less the inactive form. And T3 is the active form. What it says there is the conversion of T4 to T3 happens when you get close to the target tissue. Okay. Let me write that down for you. All right, so there you go. The main function of thyroid hormone, mostly T3, its functions increase BMR. That stands for basal metabolic rate. You just boost your metabolism. Now, an effect of that is to lower blood glucose. Increase activity level, increase your metabolism, basically, you're going to drop the glucose level. It's lipid soluble. It has receptors all over the cell, all inside the cell, cytoplasm, mitochondria. It's secreted in its inactive form, T4, 90%. But then it would be converted to T3 at the target tissues, mostly at muscle, skeletal and cardiac muscle. 90% secreted as T4. You get close to the target tissue, close, say muscle, an enzyme converts just knock off one of the iodine molecules. So T4 becomes T3. It can enter the cell and boost metabolism. Stimulation. It's thyroid. The thyroid is anterior pituitary dependent. So elevated levels of T4 would stimulate the release of TRH and then TSH, and TSH would stimulate the thyroid. And then, so falling levels would stimulate TSH release. Rising levels would inhibit TSH release. And I think we did talk about that. Now, the other thing is you need iodine for synthesis. So cells can make the protein part, but they can't synthesize elements of the periodic table. So you got to extract that from the blood. But let's say you live kind of inland in a region of the world where you're not exposed to a lot of salinity in the water. It's all fresh water. You might have an iodine deficiency in your diet, which may cause a colloidal goiter. So in that case, what's happening is, well, TSH is detecting very low amounts of the thyroid hormone, so it keeps secreting TSH, and you keep secreting the follicle, you keep stimulating the follicle cells to make the colloid, okay? But you just can't finish the job because there's not enough iodine in your diet, so you get a little goiter right there. So you can call that a colloidal goiter. And the physiology of making the thyroglobulin and then synthesizing it with the iodine, the steps are shown here. So I'm going to take you through. What we're looking at here is a small portion of a follicle with a blood vessel. So we get a bit of the colloid, the follicle cell, and then the bloodstream. T3, T4 synthesis. So the first thing you got to do is make that globular protein, thyroglobulin, shown up here, step 1. They show the ER, Golgi-R apparatus, just making the protein, and you exocytose it into the colon. You don't keep it inside the cell. It's secreted, exocytosed. They're just showing you the tyrosine amino acids, just that part of the thyroglobulin. Cell synthesizes thyroglobulin. I've been calling it inactive thyroid hormone. It's pretty much just thyroid hormone without the iodine stuck to it. Sometimes I abbreviate it THB. In particular, the tyrosine amino acids are important. Note the tyrosines. Tyrosine amino acids, and they're illustrated as these purple bars. Right? I'll draw them as purple bars, and they're secreted into the colloid. That's the first step. Then what you got to do is you got to trap the iodine from the bloodstream. That's shown on the this side of the cell. Iodine trapping. Okay. Before I proceed, I should mention all of these steps, again, are facilitated by TSH, thyroid stimulating hormone. So what I'm writing is TSH facilitates this process. When you trap iodide, well, they kind of show the, excuse me, the little green balls entering the follicle cell. They transport it across the cell, and they oxidize it. There's an enzyme that'll oxidize it from iodide to iodine. Oxidize, and they change the color from blue to, from red, excuse me, from green to blue. Okay, get that straight. So when you oxidize it, you call it iodine. So iodide is like, I think the correct molecular form is, it's an anion. Iodine is like that. Well, anyways, in the figure they go from green balls to blue balls, and then what you can do is iodinate. Okay, let's see here. So let me follow their numbers. Step 2, trap. Step 3, oxidize. Let's try to stick with the numbers on the figure. Number 4. Form MIT and DIT. You're just sticking the iodines on the tyrosine amino acids. Step 4. Formation of MIT and DIT. MS, it's like monoiodo tyrosine and diiodotyrosine. So mono 1, di 2. So for example, if it's mono, just stick 1 on there, on the tyrosine residue. There's a MIT, and there's a DIT. And then step 5, you can link MIT and DIT to form T3, T4 in the next step. Step 5, link MIT and DIT forming T3 and T4. So T3 is, well, I'll draw and you tell me what it is. That's how I'll draw the T3, so then the T4 would be T3 is a MIT and a DIT, and T4 is DIT. Yeah, then you can just, you're good to go. Now basically you endocytose that with the whole thyroglobulin thing, just engulf the whole thing. They're just showing you the part that's been iodinated with the, the tyrosines. And so that's step 6. Thyroglobulin, colloid, endocytosed. And you fuse it with the lysozyme. Thyroglobulin THB / colloid is endocytosed by the follicle cell. I won't write that, but endocytosed means cell is taking it in. Fuse with lysozyme. Or lysosome, I should say. It's a lysosome. Lysosome. Lysosomes are the cell organelle that have the chemicals that can basically cleave off your T3, T4. That's what it says right there. Okay. And that'll allow them to circulate. That's the last step. Cleave off. T3, T4, into circulation. So here's a complete, it's a more accurate representation of the thyroglobulin with the tyrosines. So the tyrosines are shown right here. And then there they are in the middle frame, iodinated. Let me point to it. You tell me, is that a mit or a dit? It's a dit. You got the two. You got dit, it's T4, right? And so you just cleave that off of there, and that's what you secrete. So in the previous drawing, they just showed the tyrosines. They didn't show the whole thyroglobulin. All right, so I'm going to move on. You have any questions about the thyroid or the parathyroid? Yeah.
There was like one little green thing, like what that would be lit, and then did the other two things. I'm just trying to understand.
The dit would have two green things, which is iodine, and the
Okay.
mit would have one.
Okay, I just wanted to make sure that was it. Okay.
Let's see here. So it happens they use green balls for iodine, and they use blue. So they change the colors, but the concept is the same. Pancreas. Where is it? Can't see it here, but if you cut along the greater curvature of the stomach and reflect it back, I can see the tail of the pancreas there. So it's located in the space behind the stomach called the lesser sac or omental bursa. Pancreas is located posterior to the stomach in the lesser sac. It's also called the omental bursa. What's it on the slide? Lesser sac makes more sense to me because there's a greater sac. It's just pretty much you open up the body cavity and just whatever's inside there, that's the greater sac. And you start looking behind things, that's the lesser sac. So that's where it's located. It's more fully shown in this dissection here. There's the head of the pancreas. This is the duodenum, the first part of the small intestine. The pancreas is very important for digestion. But we're more concerned with this endocrine function. All of the cells for the endocrine function are in these little clumps or islands of cells called the pancreatic islets. And we looked at this before. This is from another book. But there's all different kinds of cell types within the pancreatic islet. So the endocrine function, study the pancreatic islet. The different cell types in there, I'll go over next. But here's a picture from one of our slide collection. Can you see them? We did the lab in the morning class. A lot of students, they just kind of look for something that's lighter and stands out, but that's not always the case. Not it, not it, not it, not it. If you see something with a lumen and cells inside, it's probably a blood vessel. This looks like it might be part of the pancreatic duct for digestive enzymes. You're looking for a clump of cells, no lumen. And you can see all the cells are clumped together because I can see all of the darkly stained nuclei of the cells. Boom, boom. That's also it. Okay, those are probably the best ones. I think these are a couple of small ones down there. You'll have a chance to show that to me in today's lab. Okay, but I'm moving on. Let's just talk about two cell types. Don't worry about the ones on the bottom. Worry about alpha beta. Those are the ones that secrete hormones that regulate blood sugar. So alpha and beta. The alpha cells secrete glucagon. You're not expected to identify individual cells in an islet. I mean, you could stain for them, but we're not going to do that. Just find an islet on your slide. All right, so anyways, this raises glucose levels. It's a hyperglycemic agent. I say it's your exercise hormone because you need to get your blood sugar up to do your workout. Okay, so how does it do it? Let's write down these two words. You want to target tissues that have your glycogen stores. That's chiefly skeletal muscle, liver. Target muscle, liver. That's where you got your glycogen stores. And you can break down glycogen directly by glycogenolysis. But also, if you want to make carb from non-carb, that's gluconeogenesis. I defined that yet. This can do both. Gluconeogenesis. And well, what I would do is just remember that it increases blood glucose. Okay, that's the main function I want you to know. And then the other one, insulin, will decrease blood glucose. Secreted from the beta cells. Beta cell function, very important. Decrease blood glucose. All the hormones we're talking about. There's only two that have an effect where you can lower blood glucose. Insulin can do it. Thyroid hormone has an effect to lower blood glucose. Anyways, this is your major anabolic hormone. It's a tissue building thing. So insulin sensitive tissues that respond to the insulin have an ability to then take glucose out of the blood and into the cell so they could utilize it for fuel or for storage. So the target of insulin, muscle adipose. Muscle adipose. Insulin, just to have you know, there's two types of diabetes, type 1, type 2. Okay. Full name is diabetes mellitus. Now, let's say you're a child and you get some kind of virus infection, and the virus mimics proteins in the beta cells. Then your immune system makes antibodies against it and attacks the virus and your own beta cells, maybe destroying that cellular function. Now your body can't produce insulin. So when insulin isn't there and you're dependent upon injections, that's the type 1. They first noticed a small group of juveniles with that. So, it used to be called juvenile onset diabetes. Now we just call it type 1. Now the much more common one, about 95% of all diabetes cases are the type 2. That's more of a lifestyle disorder. Maybe a lifestyle of high-fat diet, sedentary, low activity levels. Insulin is there, but it's not working. Over time, your body has become insulin resistant. And if you do get diagnosed, you can be treated. The benchmark for diabetes, well, they measure the glucose, right? In the fasting condition, if the level is greater than, 125 mg per deciliter, that you're classified diabetic. Okay, so usually the procedure is you do a fast, okay, 9 p.m., 9 a.m., get your blood draw. In those 12 hours, if you haven't eaten anything, your sugar should be less than 100. Okay, they kind of don't like it when it's not. If it's greater than 100, if it's 125, 126, you're classified diabetic, and you can treat it. But anyways, it's such a major epidemic problem. I used to give a whole lecture on diabetes. Now I at least want you to know the two different kinds. Any questions on the blood glucose regulation? Remember this figure? This is the first one I showed you, I think, from Monday. Seems like it's forever ago, Monday. It's only Friday. Covered a lot of ground. But anyways, this kind of shows it, right? It's like here's the insulin, and there's the glucose. We did cover it. Okay. So what I did for you, just to start to finish up here, I was like, I used to ask this question. I'm like, hey, this is kind of hard. All these hormones and their effect on the nutrients of the body, fat, protein, and glucose, and I just table it out. I'll just give it to you. Just study this. I think this is good information to know the effects of these hormones on the blood level of glucose or on what it does to fat or protein. Yeah, so you don't have to answer that. I'm just giving you the table. One last thing I want to say is there's also diabetes insipidus. I usually don't hear about it, but this is a problem with ADH. So let's think about this. One means tasteless urine, one means sweet urine. So if you have high blood sugar and the level just can't go down, it might spill into the urine. You shouldn't see sugar in the urine. So that's why it's sweet. The ancient Egyptians used to taste the urine to test for diabetes. So thankfully we don't have to do that. Yeah, right? We have just do a little dipstick and you can just do that. In terms of this one, think about this. We know ADH causes water reabsorption at the kidney to decrease urine output. So if you're deficient in it, you would increase urine output. It'd be more watery, less concentrated, hence tasteless. All right. That concludes lecture. Done. Erase the board and take your picture.